Hello, welcome to another Stat 432 video. This video is going to sort of do two things. It's going to do more than that, but I want to talk about two things first. First, it's going to sort of amend the previous binary classification in our video, because I think I made things more confusing than they need to be. And then this will also serve as an additional example. This code that you're seeing here might look familiar, and that's because it comes from a quiz question on the most recent quiz. If you are watching this video in the fall 2020 semester and currently taking Stat 432. So we're going to walk through this example. I'm giving away an answer, but I think it's important enough that I correct the record, that I do it with an example that you're already familiar with, because you'll better understand it because you've already thought about this problem. Okay, so what do we have here? So we're going to use the German credit data set from the Caret package. Here we are loading that and then coercing it to be a Tibble, and then storing it. We're then test train splitting it. We could check the documentation to see what this data is all about, but we're not really thinking about this data from an analysis perspective. We're really just all about calculating metrics for binary classification here, so we're not going to dig too deep into that. There are many variables in this data set. We're going to use the class variable as the response variable. We need to check what levels it has in a second, but we're going to call whichever one is the bad one the positive class. A lot more on that in a second. Okay, so we're going to fit a decision tree to the whole training data set. Again, class is the response. We'll use all the other variables as feature variables. And then with that model and the predicted probabilities it gives us on the test data, we're going to make two classifiers. One with a cutoff of 0.5 for the positive class, and one with a cutoff of 0.8 for the positive class. And then once we do that, we're going to calculate the test precision and the test false discovery rate for both of those classifiers. I'll enter it here. I'll see if I got it right. I'm doing this sort of live-ish so you can see me make mistakes. Hopefully not, but if I do, I'll correct them and you can sort of see some of the process. Okay, so there's a lot of confusion about how to calculate these binary classification metrics, and it's a little bit my fault, and it's a little bit your fault, although let's put most of the blame on me. So a couple things happened that are probably confusing a lot of this. If we have a look at the notes here, in the notes, I'm using 0, 1 for the two possible classes, but then I'm implicitly saying, well, 1 has to be the positive class and 0 has to be the negative class. But that's kind of not true. The positive and negative labels can be pretty arbitrary, and that's maybe something I'm going to break down a lot in this video. The other thing that's very much my fault is that I introduced a new package, which I didn't have enough practice with myself, and I made a couple of mistakes in the video when discussing it. And then, or not mistakes, I just sort of misstated one thing that isn't always true, and then that confused people. So I'm going to correct the record on that. But so what I want to say is that of everything that we're doing here, the most important thing is the definition of true positive, false negative, and true negative, right? So a true positive being when it's actually the positive class and we predict the positive class, and so on and so forth. I was careful not to use 0 and 1 there, and instead refer to positive and negative. But so what I want to sort of like get across in this video is that as long as you know those definitions and then have access to definitions like these, you can calculate anything you want. And furthermore, being able to do that quote unquote manually is probably better than knowing how to do it with a package, because as we've seen, some packages can be confusing to use. But all that said, the way to do, this problem is to just calculate this metric. Now, the trick is that you need to know how to do that. And what I'm going to try to show is that if you rely more on the definitions than packages, you're more likely to get it right. So basically, I want to do this problem like 3 main ways and then like 2 subways within each of them. So I want to do what I'm going to call manual procedure. I want to do the CVMS evaluate procedures. That's using the CVMS package and then the evaluate function within it. And then at sort of the request of some other students, I think Fusion Matrix, I want to use the confusion matrix function from the caret package. That is not misspelled. Okay, at least I don't think so. So that's my goal. This might be a really long video to do one problem, but I think it'll be worth it. I should note this is literally the 4th time I'm recording this video. I've had every possible... well, in addition to me making a mistake in one of them, I've had every possible tech issue go wrong. So I'm praying that my laptop holds together this time. It's been having some battery issues, even though I'm plugged into a charger, but we don't need to worry about that. Okay, let's do it. So, let's run the starter code. For a second, I thought it wasn't running. Okay, so long story short, there's a ton of variables in this data set, but we care, most importantly, about the response variable, which is class. And this is where all the confusion is stemming from, is right here. So let's think about this. We have 2 possible categories here. We have bad and we have good. And this is incredibly confusing because bad and good and positive and negative are incredibly related, but I think the confusion there will lead to a better understanding. Okay. So let's ignore positive and negative for a moment. I just want to talk about how we would think about this problem if we were doing logistic regression in R. And when you do logistic regression in R, the order of these levels matters a lot. Whatever is the first level here, that's considered y equals 0 in our mathematical understanding of logistic regression. And by process of elimination, whatever is the second level, well, that is what we refer to as y equals 1 in our mathematical notation and understanding of logistic regression. A side note here, the order of these levels is arbitrary, and you can even change it. I don't recommend it this time. But by default, R will order them alphabetically, but they don't have to be alphabetical. That'll come up when we look at the documentation of this package, and there's actually a minor error in the wording of the package, which I'm talking to the developer about, but we'll come to that later. But suffice it to say, first level is 0, second level is 1. Okay. But this is arbitrary. We could swap these, but just by default, that's what R is going to do. And that's sort of important here. Everything is arbitrary that we're doing, but we have to understand the decisions we make and the ramifications therein. And then the problem says, arbitrary definition, if a loan is labeled bad, we're going to call that the positive class. So it's almost like those are the ones we're looking for. In a sea of all the loans, we're looking for the bad ones. And that kind of makes sense. So in the sort of positive negative nomenclature. So bad is positive and good is negative. A little confusing, admittedly, but I think that'll be good. Okay, so I want to do this manually, quote unquote. And I assume you're going to be watching this either Thursday, Friday, Saturday, or Sunday, which are the 4 days leading up to the exam. Unless you're watching this in the future, in which case, hi from 2020. I would recommend doing it this way. I think you'll see that there's less room for error, and you're not sort of relying on a package to do a thing you expect it to do. You're just going to write the code that says exactly what you want. So let's do that. So we're going to fit a model. What was it? Class was the response. We're going to fit to the training data. And I think it said, excuse me, keep all the default tuning parameters. Let's just check that real quick. All right, that's ugly, but that's a tree. Let's store that. Okay. So now let's make quote unquote predictions. And let's just give it the test data like this. Okay, so note right away, had this been logistic regression, it's not, it would have given us this column. But our part, it gives us both, and we can kind of use one or the other. So I'm going to say, well, I'm going to sort of stick with the logistic regression mindset and say, well, I'm just going to focus on the probabilities for the good class. So I'm going to extract that column like so. And then I'll store this as prob. Okay. And now I want to make classifications based on that. And right now we're going to work on this. So 0.5 for the positive class would also be 0.5 for the negative class, assuming none of the probabilities are exactly 0.5. And we're just going to ignore that because it doesn't happen in this data. And in practice, it wouldn't make a huge difference, but you should be careful about that. But for the sake of the exam, you can assume that none of the probabilities are going to be 0.5 or 0.8. Okay, good. Okay, where was I? Oh, right, making classifications. Okay, so I want to look at these probabilities and find when they're bigger than 0.5. That is, find when probability of y equals 1, that is the good class, is bigger than 0.5. And then we can wrap that in an if-else. And so when that's true, output good. And when it's false, output bad. That looks good, except it's not a factor, so let's do that. So it's very similar to the response variable. Okay, good. It's a factor, and it has the same levels, and they're in the same order, which we see right here. Okay, that's good. So I'm going to call this pred. Okay, great. So now what I want to do is, with those predictions, calculate the relevant metrics, right? So what are those metrics? Precision and FDR. And I'm not too smart. I don't have a great memory. So I need to look these things up. Turns out that at least one of them is on here. Actually, two of them are on here, but more on that in a second. So FDR is staring at us right here. And we see that FDR is based on false positives and true positives. And we don't see this thing called precision on here, but if we go to our good old Wikipedia article here, it says that precision is also the positive predictive value, which is based on true positives and false positives, which is, exactly what we have here. Minor note, for the sake of the exam, I'm not going to ask you to calculate something that's not on this page. Or if I did, I would define it for you when it comes to binary classification. So you don't need to be referencing things you're not supposed to reference. And we're not trying to trick you. The most important thing, which is what I'm going to do next, is realize that, well, all these metrics are based on true positives, false negatives, and true negatives. So I'm going to calculate all those things right now. So let's do that. So let's start with a false positive. Something like that, which we'll call false positive. So that's when the actual value is positive and the predicted value is, the actual value would be negative, and the predicted value would be positive. That is what a false positive is. We say it's positive, but it's not supposed to be. Okay, great. So, but in the terms of this example, good is the negative class, and bad is the positive class. Okay, but now let's actually do this with code. So in the test data, so the actual values, these are the actual values, and we want to find when they are equal to good. Okay, great. And then in the predicted values, we want to check when those are bad. And these are when those things happen at the same time. Therefore, these are the number of times that occurs in the test data with the classifier that we're using. So let's call that a false positive. Okay, I'm not going to write this out for all the other things, but let's do them quickly. So a true positive would be we predict positive, but it's also actually positive. So something like this. What's next? We'll do false negative. So false negative. So that means we're predicting negative, which is good, but it's false. That is, it's not what it's supposed to be. So the actual value is bad. And so what's left? True negative is when it's actually negative and we predict negative. I'm going to run that, and then I'm going to output it by looking at this. So false positive equals false positive. So what I'm doing here is I'm creating a named vector just so things are slightly easier to see. True negative equals true negative. Okay, cool. And then one check to make sure I haven't, screwed this up really badly is if I sum that up, it should be equal to the number of rows. That's not number of rows in the test data, right? So where is that? Here. That doesn't look right. Aha, so I've screwed it up. Okay, so that means that one of these definitions is wrong. Who would have thought? Okay, so false positive is when we predict bad, but it's actually good. That's good. True positive, when we predict positive, but it's actually positive. Okay, that's good. False negative. I see the problem already. We predict negative, but it's actually positive. And true negative should be we predict negative, and it's actually negative. So we'll run that. Now things look better. Okay, good. Sanity checks. Good to have. All right, there we go. So now we just need to calculate those two metrics, which again were these two here. So I'll say the PPV, positive predictive value, is the true positives divided by false positives plus true positives, and good enough. The false discovery rate is like this. And then I will wrap these in parentheses so we can both store and output these numbers and something like this. Okay, so at this point, I want to check that I'm not too far off. So let's throw these in here. And then we'll sort of just throw some random numbers in here. Okay, so I know it's fun if I make a mistake so I can correct it, but I really hope this is right. Okay, wonderful. Okay, great. So, I mean, whether or not you do that in a Prairie quiz is up to you, but now let's move on. Okay. So, now this statement here. This is tricky because I've already made an arbitrary choice, which is that I wanted to do this based on a probability of whether or not it's good, which is the negative class, but this cutoff is for the positive class. So what I cannot do is just this. That's not going to work. Actually, why don't we just do it real quick? So I think we'll find that this number is not this number. It's not. Oh, this is an interesting number. Anyway, so the problem is that this says classify to good if the probability of good is bigger than 0.8. But that's not what we want. So what we want is this. And first we'll show that this gets the right answer and then verify this to ourselves. Okay, so I like to run from the beginning. Aha! 0.5, 0.5. Prairie Lawrence says 0.5, 0.5. Great. But let's do this a different way. Let's comment this out. So why not just do exactly what the problem says? So to do that, what I'm going to do is deal with the bad, quote unquote, bad probabilities because I can. I'm an adult. I can do what I want. Now, if you were doing logistic regression, you'd have to do a 1 minus in there somewhere, but that's not all that hard, right? Okay. And then to do the predictions, let's steal some code here. So now these probabilities are based on the probability that it's bad. So we can just use the cutoff as stated. Change this to, well, if the probability that it's bad is bigger than 0.8, classified to bad, otherwise good, except spell it correctly. All the other code is the same because these are basically just definitions. You could even write a function that does these kind of things. Okay, that's great. Let's run this. There we go. The right answer. Cool. So I guess what I'm trying to get at is a couple things here. One is if you do it manually, you can kind of just do whatever you want. And you can do things like just write down simple definitions and then calculate the metrics based on them. And you can do some nice little checks like this. Okay, great. So there's part of me that wants to just end the video right here and say, ignore what I showed you before with respect to these other fancy functions and all that stuff. And honestly, if you want to turn off the video right now, more power to you. I would approve of that. But I'd like to show how to do those other things to see how... I mean, I might screw it up still, so we'll see. Okay, so now let's use the evaluate function from the CVMS package. So let's load that package, CVMS. Okay, great. So the trouble here is, well, let's just go straight to the documentation, and we'll see, one, a problem with the documentation, and two, a problem with what I did last time. Oh, you might notice I have like a tri-pane layout here. That's because I'm on the preview version of RStudio 1.4, which was released, well, yesterday now, because it's after midnight, but you get the point. Anyway, so if you're interested in that, have a look. But here we go. Okay, so blah, 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 blah. Importantly, we need to read right about here. So when type is binomial, that's how this package is talking about binary classification. One column with the probability of class being the second class alphabetically. So what it's saying is it wants probabilities for it wants probabilities for this class. And then the cutoff internal to evaluate is going to be based on those probabilities. So you have to use the good probability here. You have to use the y=1 probability, even though it's not the positive class. Okay, so that's where a lot of the confusion is coming from. I would also note that this sentence is technically incorrect. That's that note about alphabetically I said. It's not the alphabetical order here. It's the second element that matters, but often they're the same because by default, R will make the factors in alphabetical order unless you go out of your way to change it. But that is a minor note that you should keep in mind. Okay, so with that in mind, I'm going to try to do this. And what this package expects, first I need to make a tibble, or data frame, whatever you want to call it. I'm going to call this the actual value is these things here. And then we'll call it prob is equal to prob. And I'm doing this just because this is the sort of thing that the evaluate function expects. So I'm going to call this results. An arbitrary name, but it's okay. All right, so now evaluate data. This thing here. Cool. Next up, target column. This one. Prediction column. This one. What else? What else? What else? Type. Ooh, we gotta tell it it's binomial. What else? Cutoff. We're gonna do 0.5 for now. What else? What else? What else? Aha. Positive class is going to be bad. And I don't think we need to add any extra metrics, but we'll think about that in a second. Okay. This line of code is far too long, so we use a handy trick, an exercise for the reader to figure out how to do that. I might tell you in a future video. Okay, so let's run this. Does everything look good? Does everything look good? Oh, well, except I skipped a really important step. These probabilities are from here. we need to go back and do this. I should take this and put it here, right? So we need to, based on what we read in the documentation, extract the probabilities for the good class. We don't need this because that's going to happen internally in this function. And whether or not it's probably, and this line right here is probably the reason that you should use the manual method, because you're doing this instead of allowing the function to do it. Okay, so fit the model, get the probabilities for the second class, for the second level of the factor that is the response. Make some results. There it is. That's just getting the formatting right. Let's run this. Okay, it runs. I believe this positive predictive value is this positive predictive value, but we should probably dive in a bit further and check that out. So I'm going to call this eval underscore results, something like that. So let's do this. Eval underscore results $, positive predictive value. That looks like that. By definition, so unfortunately, I think FDR is not in here. There might be a way to add it, but from what we found earlier, FDR is also just 1 minus this. That's the same as this. Cool. Right? Okay, but now, remember, the second part of the problem asks for a cutoff of 0.8 for the positive class, which is bad. But this function, when it goes to make classifications, it thinks in terms of the second level of the factor and its associated probabilities, which it expected us to supply. So we need to use the 0.2 cutoff. And then when we run this, we see the answer here. Cool. Okay, so hopefully that makes... Oh, I guess maybe one more thing I'll do real quick. Eval underscore res $, confusion matrix. So I think this is actually really important, right? So if we ignore this column and this column, what it does is it creates this data frame here where it has bad, predicted bad, actual bad, predicted good, actual good, or actual bad, and so on and so forth, and how many of those occur, right? And then that's just based on making classifications based on the cutoff value, based on the good probabilities, right? But then after that, it comes in and says, okay, well, you labeled this class as positive and this class as negative. And it actually, so depending on which of those you do, it shows you which ones are the true positives and true negatives. So, but that's that's the whole point here, is that these things are all you need internally to make the classifications, but then these ones give them the characteristics that make it a true positive or whatnot, and then that's how you calculate the resultant metrics. Hopefully that's a lot clearer now, but hopefully maybe you just don't even want to do this. The reason I liked this so much is because of the ability to plot the confusion matrix really nicely, which we saw in the other video, but I'm not even going to do that now. Okay, let's do one more way. And again, hop in the time machine, go back to when right before I started showing you the evaluate method, and just pretend that's all you knew. But if you're still with me, I'm going to show you one more way, but you should probably just ignore it. But in case you like it, you can do this. Okay, so let's steal some code. Okay, so what am I doing here? I am fitting a model. I am extracting the bad probabilities, the probabilities for bad. They look like this. And then based on that, I am making classifications, classifying to bad if the probability of bad is bigger than 0.8. Okay, cool. So now I'm going to use this function. And I would suggest you read the documentation. I'm going to try to do this based on a little bit of memory, and then if I screw it up, we'll go to the documentation. Okay, so I'm actually going to load the library so that I can get the autocomplete, I think. Okay. Okay, so data. So data is the true values, and that right away makes me not want to use this package because that's confusing to me. I much prefer the nomenclature here. And then the reference is the predicted values, which is here. And then lastly, we have to specify the positive class, which is bad. Okay, did that work? I don't think so. Okay, so here we see our confusion matrix. And my positive predicted value is not something I was expecting. If I have to scrap this video now, I'm going to be super upset because I spent so much time on it. Okay, what went wrong? Fit the model. Get the probabilities based on bad. If it's the probability is greater than 0.8 that it's bad, we get bad. If not, okay, let's check these things. Oh, maybe I may have swapped these. All right, we got to check the documentation. Who am I kidding? Okay. Data, a factor of predicted classes. I guess reference makes sense as the true. Okay, I still don't like those names. They're confusing to me. But you live and you learn. Okay, that's good. Run it. Positive predicted value, 0.500. While we're here, just to show you, I could also do it based on the good probabilities, except now we need to make this good, this bad, this 0.2, run it, check it, still good. And that's to sort of show you the arbitrary nature of just, you can make almost any decision you want, you just need to know the correct adjustments to make based on that. Oh, I guess while I'm looking at this, let's call this caret results. So you'll know. I mean, it doesn't matter in this case, but you'll notice that these values are sort of rounded because this is being printed, not sort of returning the exact thing. But so you can access things like this. So if I do caret results $sign. So some results are stored here, things like accuracy, or if you do by class, so that's like within columns or rows, though it's things like sensitivity, positive predictive value. What else is in here? Table. Aha, yeah, that's like the table, the cross-reference table. We told it that, but in this case, what we want is here. Okay, so yeah, I guess this video wasn't quite as long as I thought it was going to be. It probably helps that I made it 4 times, so I cut down on a lot of the fluff. But yeah, so I hope that really clarifies what's going on here. But I guess before I sign off, I just want to reiterate that what is a true positive, false positive, true negative, and false negative is what I really want you to know. And I know it says 0 and 1 here, but that's arbitrary, and that's actually separate from positive and negative. But the definitions of true positive, false positive, they're not all that hard to understand, I think, right? True positive, that's when you predict positive, and it was actually positive. False positive, well, you predicted positive, but it was actually negative, and so on and so forth. And then most of the interesting metrics are functions of those things. So as long as you can get those 4 quantities, you can calculate anything else you want. In practice, if you weren't trying to answer quiz questions, you probably want to move into a system, but we're not really there yet in this class. When we do get there, we will just buy into a system wholesale and use it. But for now, I would suggest this method, but you're welcome to do either of these if you're comfortable with it, but that's a choice for you. Okay, we made it. I'm happy that my laptop didn't die this time. I'm actually ecstatic. Yeah. So yeah, as always, if you made it to the end of the video, good job, and I'll see you in the next one.